So for today's session, I've prepared a little bit more of a deep dive on the optimization side and the potential types of use cases we can explore with a neutral atoms type system within this field. In order to start off for that, there are a couple of things that we need to keep in mind. And for that reason, I wanted to start off the session with talking about hybrid algorithms in particular, and as well as how to measure the complexity of certain methods and certain algorithms. So when we talk about quantum computing in general, we have seen it in the very, very beginning as the introduction, that we typically distinguish two regimes, two periods, I would say. The first one corresponds to the current actual status of quantum computers, referred to as NISQ, so noisy intermediate scale quantum, which represents the current stage of maturity of quantum computers all across the board, not just for neutral atoms type systems. For this, as the name implies, NISQ, so noisy intermediate scale quantum, means that there are error rates, significant error rates with the manipulation of quantum information. Therefore, noise mitigation and error mitigation techniques are very, very welcome, as well as the size of the system is prohibitive to tackle large problems, in a lot of cases, industrial size problems even. For this reason, the current and I would say immediate future deployment of quantum computers is targeting what we call the high performance computing or HPC sites. So we discussed it last week that the role of a quantum computer is to provide an extra supplementary computational resource to complement the power of CPUs and GPUs and potentially other emerging technologies. So it is really about dedicating the right computational resource to the right task. And in particular, what this schematic representation illustrates is that quantum computers live hand in hand together with classical computers. Therefore, the solution strategies we envision for a specific problem can potentially leverage this synergy, this integration of a quantum systems as part of a more classical, more conventional workflow. Hybrid methods represent this. They incorporate this in essence and in actuality as well. When we talk about hybrid methods, what we mean by hybrid is a quantum classical algorithm, meaning that your algorithm, your solution strategy is divided into two parts. There is a first part that's dedicated to a conventional classical computational resource, and the second part that's dedicated to a quantum computational resource. How this division is done is determined by the type of algorithm you want to deploy. Typically, when we talk about hybrid methods, the first examples that have appeared and that can come to mind are variational methods. So a schematic representation here is illustrated on this image. The idea here is that you use what we call parameterized circuits or parameterized functions that are being updated after each iteration by a classical computer, and then they are getting executed on a quantum computer to provide some feedback for the optimization loop. Essentially, what you are doing is a type of optimization method in which the objective function is executed on a quantum computer. Meanwhile, the optimization step determining in which direction you are headed to find better parameters is carried out by classical conventional methods. This is a typical example of dividing the available computational resources intelligently to dedicate tasks that are easy or relatively easy to handle for each of the devices. As you know, CPUs and GPUs are quite adept at handling arithmetic and simpler linear algebraic notions like matrix manipulations, while QPUs have a much more focus on more abstract and more complex computational cycles. And these variational methods are a very, very good example of this division of tasks into two parts, but this is not the only way to go about. In general, variational methods rely on a very, very similar architecture, but can be deployed on various different computational devices. So the quantum part of the objective function itself can be tailored to represent a digital quantum logic gate-based implementation or an analog or even annealer-based representation as well. Typical applications for variational methods involve chemistry-based computations, solving linear systems of equations, or even performing quantum simulation-based experiments as well. One key point about variational methods is that it is really leveraging the fact that a quantum computer is limited in its computational capabilities and requires assistance from classical computational resources in order to enhance its functions, to find an optimal parameterization in a sense. Therefore, this is really an algorithmic construct that's relevant as long as quantum computers themselves are not powerful enough. So variational methods and in general, most hybrid methods, so hybrid quantum classical methods, are predominantly what we call NISQ-centric constructs. So they are really tailored and meant for deployment in this earlier stage, in this noisy intermediate scale quantum stage of the technology. As we are going to move towards fault-tolerant quantum computing, their impact will gradually decrease. They will never properly vanish because, of course, classical technologies are still advancing. We are producing better and better microchips still, but there is a limitation to Moore's law. There is a limitation of what we can achieve with conventional computers. So we are expecting to gradually decrease the impact of these methods. Nevertheless, in the near future, we are really working with these type of methods. An additional key feature about hybrid methods is trying to determine what's the actual impact. So from an algorithmic perspective, and they are really tailored for the current generation of the devices. But what typically people ask is, what are the performance metrics? So what is the potential outcome of a hybrid method? How can I study? How can I evaluate the potential impact of a hybrid method? And in order to evaluate the impact, we need to take a little bit of a closer look on how mathematicians, how people define what's an easy problem and what's a hard problem, because that's the foundation layer on trying to establish what kind of advantage, what kind of gain you can expect from an algorithm. So from an algorithmic perspective, everything needs to be objectified. It's not heuristic. It is really based on mathematical computations. The foundation of this is what we call complexity theory. So this is a specific field of mathematics that was introduced in the 40s, the 30s and 40s, in order to rigorously study what we mean by a specific problem. And so what's the definition, a mathematical definition of a problem? What's the mathematical definition of a solution? And what are the computational resources required to obtain this solution. The key important part of this is that complexity theory, so being able to tell if a problem is easy or hard, has been established with the fundamental principles of classical computers in mind. So when complexity theory was created, it was hand in hand with John von Neumann's vision of what a classical computer should be. So the whole theory was built around manipulating information in a classical way. Therefore, when someone tells you that they have this hard problem, the hard problem they mean is a hard problem for a classical computer, because mathematically that's the definition that was given to it. So we are going to go through a couple of what we call complexity classes in order to group together types of problems that are as easy as one another or as hard as one another. However, all these initial notions are really meant for classical computers only, and for quantum computers, the whole definition, the whole foundation needs to be changed. So this diagram is a schematic representation of the most well-known problem complexity classes. So whenever we talk about how difficult a problem is, you might have seen some of these mentions. I will give a quick definition of a couple of these classes. The most well-known here is in the middle on the P class with violet or purple color, P standing for polynomial in time, meaning that these are what we call the easy problems that we can solve more or less quickly. And then going broader and broader, problem classes become more and more complex in a sense. With the dashed categories, however, you can see already two mentions, the BQP and the QMA, which are complexity classes that have been established with the foundational basis of quantum computers in mind instead of classical computers. So people have already started introducing in recent years mathematical definitions to classify problems for quantum computers and how difficult it is to solve problems for quantum computers, not just for classical computers. It's still developing and evolving field of mathematics. So there's a lot of unknowns, even from a classical side. You might have heard about this. One of the 7 famous millennial problems in mathematics is actually asking about whether 2 of these complexity classes are one and the same or not, just as out of curiosity. So to give you a couple of definitions to illustrate these complexity classes and what we mean by easy and hard problem, let's start with the simplest. So the one I mentioned beforehand, the P problem complexity class or polynomial in time. So this means that this is a problem that for which we know a solution that can be executed in a time that scales polynomially with the number of the variables or the number of inputs. So this is when we talk about linear or quadratic algorithms. And these mentions refer to the fact that if you add more data, more input variables, this will multiply the time required with a certain polynomial function in mind. So there are quite a few examples that fall into this class. And once again, this is having classical computers in mind for this. So it's really based on how you manipulate classical information and how you execute classical algorithms themselves. So I've given a couple of examples, much like linear programming that we have seen beforehand. Decision problems and whether something is a prime number or not, that you can find as a basic concept of security, a couple of graph theory problems, and some other interesting problems as well. broadening the category to what we call a NP problem or non-deterministic polynomial in time. So these are problem classes for which we do not necessarily know how to efficiently solve, but if you are given a solution candidate, you can quickly test if that solution candidate is indeed a solution. That's what we mean by verifying the solution, verifying and the answer to confirm that it is indeed a solution. This goes hand in hand with finding a solution or checking if a proposed candidate is a solution. These are two phases that go hand in hand from an algorithmic perspective. Moving a little bit even out there, one of the more interesting problem classes, and this is typically what's referred to as hard problems or complex problems classically is what we call NP hard problem. So again, non-deterministic polynomial time hardness. It means that these are problems that are as difficult to solve as the most difficult problem within the NP class. So complexity theory has this weird notion of trying to relate problems and trying to reduce problems and solution strategies from one to the other in order to connect them with each other. This is a very, very famous complexity category because it entails a lot of the industrial deployed problems. And the implication here is that we do not know efficient strategies, efficient algorithms to solve them exactly. We only know methods to test if a solution candidate is given to verify that the solution candidate is indeed a solution or not. And I also wanted to talk a little bit about the EXP, so exponential time problem class, because this is sort of the culmination on the complexity side. So these are typically what we can classically consider the most difficult problems, because for this there is proven a mathematical proof that establishes that the solutions, the solution strategy scales exponentially with the size of the input, meaning that very, very quickly you can find yourself with infeasible amount of scenarios. So typically a lot of game theory options, game theory problems fall into this category. So I mentioned a couple of them, playing chess, checkers, or Go, or a lot of other games fall into this problem category. These are reputed to be some of the hardest problems out there. From a classical point of view. So all these P, NP, NP hard, EXP, these have existed for 50 to 60 years already in the scientific literature, and they all relied on the notion of how we compute classically. Now, if we involve quantum computers in the fold, then suddenly the whole situation becomes much more complex because information works differently. Therefore, you cannot just simply apply the same complexity categories. For this reason, people have started introducing new complexity classes, new definitions of what it can be meant by an easy problem for a quantum computer or a harder problem for a quantum computer. So BQP is the extension of what we mean by a polynomial in time or an easy problem for a classical computer, but in this case for a quantum computer. BQP stands for bounded error quantum polynomial time. So this leverages the fact that quantum information has a probabilistic notion, probabilistic part to it, and therefore capturing the right solution needs to be measured by probability theory tools as well. So it gives bound probability bound on the likelihood on finding the right solution for a known method. This BQP is interesting because we have quite a few famous quantum algorithms that are proven to be in this class. So Shor's integer factorization that has existed since the 90s, and that's the fundamental reason why quantum computers in turn will pose a danger in current cybersecurity measures, is proven to be in this BQP, bounded error quantum polynomial in time. The Harrow-Hessedin-Lloyd algorithm that is used for solving linear system quite efficiently is proven to be in this category, or Hamiltonian simulations in general fall into this problem category. So why it's interesting is it's interesting because problems that are classically known and proven to be difficult to solve with this notion of NP, or in some cases even EXP, now find themselves in a complexity category that proves that they are a quantum, from a quantum perspective, easier to solve. So polynomial in time to solve. And whenever people are talking about an actual quantum advantage, they, from a mathematics perspective, mean that the solution they deploy leverage this fact that classically it is known that it's hard to solve. From a quantum perspective, it has been proven that it's easier to solve. However, we are still waiting for actual large-scale implementations of most of these methods. Finally, I also wanted to mention another interesting problem category that's much more all-encompassing, that is called the QMA, Quantum Merlin-Arthur. So this is sort of an extension of the classical NP, the non-deterministic polynomial complexity category. And this sort of is an equivalent of being able to say that if you are given a solution to a quantum method, you can check it in polynomial time that this is a solution with a relatively high probability. So it's placed into the verifiability, the verify part of the solution. So it doesn't mean that you can easily find a quantum solution, but once you're given a quantum solution, you can easily check if it is indeed a solution. We have quite a few problems, again, known algorithms that fall into this larger complexity category as well. So why did I talk a lot about these complexity classes? The key point here is that the difficulty to solve a problem is based and is measured by rigorously establishing the time it takes, the resources it takes, depending on the computational resource it is being deployed on. Therefore, for hybrid methods who rely both on classical and quantum computational resources in order to solve a specific problem, mathematically measuring how complex they are or how efficient they are is almost impossible, because you would need to rely on two different notions of information, of manipulating information at the same time. So it would imply that you would need two different mathematical systems to try to study them efficiently. For this reason, evaluating how well a hybrid method is performing is fundamentally heuristic, fundamentally experience-based. It is very, very difficult to establish rigorously, to give a mathematical proof of how much time it would take for a hybrid algorithm to be executed for this, due to this duality, this mixed relationship. This is what makes hybrid methods quite hard to study, because the only reliable way to measure their efficiency is to deploy them. But then deploying them depends on how good you have constructed and how well you have divided the tasks into something dedicated to a classical and something dedicated to a quantum computational resource. Nevertheless, hybrid methods are still interesting and an important part of problem solving, especially for optimization problems, mainly due to the fact that for optimization problems, and this is going to be the main objective here and what's to come, we know that finding an exact solution, finding the correct solution is quite challenging. So even classically, a lot of the existing methods rely on heuristic approximative algorithms instead of exact solvers. So we are not necessarily interested in finding the best solution, but we are interested in finding a good enough solution. With this in mind, deploying hybrid algorithms or deploying quantum methods can have an immediate impact in increasing the quality of the solution, or alternatively, and more interestingly, quantum components can also bring around an impact in proposing a portfolio of solution candidates. So here we are relying on the inherent parallelization aspect, which relies on the fact that quantum solutions are inherently probabilistic. So you not only get a single solution out of it, but you get a set of solutions from it at the same time. And this is something that can be a key performance metric for evaluating and for deploying these type of solutions. With that said, let's take a closer look at quantum solutions and quantum optimization methods in particular. For that, we need to revisit, first of all, what we mean by an optimization problem. In particular, you have most likely heard about QUBO type problems. So QUBO stands for a quadratic unconstrained binary optimization problem. So it is quadratic in a sense that it has terms involving two variables. It can also have terms involving one variable and zero variables, but the two variables are the highest degree involved. It is unconstrained, meaning that there is no extra constraints. There are no additional inequalities involved with it. It is binary, meaning that the variables, it means that the variables themselves are zeros, zeros and ones in particular. Why we typically talk about QUBO type problems when we talk about quantum methods, the reason for this is that QUBO problems can be naturally translated to Hamiltonian systems, which then tend for an implementation with analog methods, or more generally, QUBO type formulation. So it involves matrix representation, and for matrix representations, so these advanced linear algebraic notions can be formulated using operators, and which also is the backbone of the Hamiltonian representation. And these operator-based representations can quite efficiently be encoded into formulation that's adapted for quantum computers. There are different strategies to go about this. I will illustrate and present two methods in particular for this. The first method I want to illustrate on how to solve these QUBO type problems or the underlying Hamiltonian formulation of the problem is what we call adiabatic evolution. So we briefly discussed this when we've seen a couple of implementations. Adiabatic evolution relies on the fact that we are instilling a slow evolution of the energy of the system from a known initial ground state, so what we call a trivial Hamiltonian, and we progressively manipulate the parameters, make the system evolve towards the target Hamiltonian. In this case, the target Hamiltonian is what encodes your actual problem, and your problem solution is the energy that comes out of it. Since you're manipulating physical systems, energy tends to be staying at its lowest stage. Naturally, it gravitates towards what we call its ground state. Therefore, if you do the manipulation slow enough, this evolution slow enough, you can ensure that at each step of the evolution, you are still staying at this ground state. Therefore, if you have started from a known initial state and targeting the problem solution, if you're given enough time, you can reach it step by step. This is the heart of adiabatic evolution and, in general, the quantum adiabatic algorithm that you can use to solve optimization problems that have this Hamiltonian representation, that have this energy and this advanced linear algebraic representation. Not all optimization problems adopt this formulation, but most of them fall within this category still. The other way to go about this is called a quantum approximate optimization algorithm. We are going to discuss about that a little bit later because it has an extra step involved on top of the Hamiltonian representation. To give a little bit more detail on these two approaches, the adiabatic method and as well as the quantum approximate optimization algorithm, as I mentioned, both of them rely on the Hamiltonian representation, on the operator-based representation of an optimization problem. In the case of an adiabatic evolution, as I said, the idea was to start from initial known Hamiltonian and then move progressively towards the target Hamiltonian, taking your time into ensuring that your solution stays at the ground state at each evolution step. This evolution for analog quantum computing can be continuous in time, so there is no discretization involved. However, as most quantum computers have been envisioned with logic gates and quantum circuits in mind, for a digital setting, and this continuous in time evolution is not something that it is feasible. Therefore, people have come up with an alternative way to handle it, which relies on this approximation. So instead of incorporating this evolution of the Hamiltonian as a function of time, you decompose it into step-by-step evolution using two main components. So the first, you can see this decomposition here with a mixing or mixer Hamiltonian and a cost Hamiltonian. The cost Hamiltonian typically incorporates the target function. So that is something that arises from your problem formulation. The mixing Hamiltonian ensures that at each step you are involving, you are discovering and you're exploring the state space sufficiently. So typically a mixing Hamiltonian involves large entanglements or entanglements of large blocks or chained entanglements in order to be able to explore the state space as efficiently as possible. These two Hamiltonians come side by side, typically in an iterative fashion, and this gives rise to specific quantum circuits that can be modeled in a digital setup, but less native for an analog type of setup. To illustrate this, you can, for instance, consider traveling salesman type problem formulation. So for those of you who are less familiar with this, traveling salesman problem relies on the fact that you are given a map. From a graph perspective, it can be a large graph, but we will talk about the optimization formulation of it. The objective is to find an itinerary, find a route to visit all the nodes of the graph, all the while minimizing the cost of the travel, so minimizing the weights on the different edges of the graph on the edges that have been selected for this specific itinerary. So it is inherently a minimization problem that involves weights, that involves the cost of travel, and that involves indicators that designate which city we are visiting at what point. So for the optimization version of the traveling salesman problem, your variables are these city indicator that have two indexes that indicate at what point in your itinerary are visiting which city exactly. So if it has a one value at a specific double index, it means that at that specific position, you are at that specific city itself. Otherwise, it will be 0. Therefore, the formulation is the following. So you have the cost function in the bottom that actually defines your itinerary, your route that's measured by the edges, the connection of the itinerary with the next step. That's the internal sum multiplied by the weights, the cost of the travel on that section of the route. And it is not an unconstrained problem because you need to respect the fact that each city has been visited once and each position of the itinerary only has one city. So you cannot be in two cities at the same time, for instance. With this, all mathematical parts of the problem formulation are in our hand, which can then be formulated in an unconstrained version as well. So this is a very, very important technique in optimization theory, is that whenever you are given a constraint, so for instance, here the fact that you need to visit each city exactly once, you can encode that constraint into a quadratic part of the cost function with what we call a penalty term. So here, what we have done is we have as objective to minimize the first term, which is the actual cost of the road, of being on the road, of traveling around as a specific itinerary. And then you have two extra terms that incorporate the constraints of visiting only one city and visiting all the cities exactly once. And these are penalty terms because there is this B constant in the beginning that's sufficiently large in order for the optimizer to favor solutions that respect the condition. If the condition is respected, then the internal part of the penalty term is 0, so there is no penalty added as long as you are expecting the condition. This is a very, very ingenious way to incorporate constraints into a problem formulation, and therefore you can bring a lot of the different constraint optimization problems into an unconstrained optimization problem formulation. This is just one example. What I wanted to illustrate now, and I will shift to the pulsar environment that we were looking at previously on Monday session, is to see how you can go about and implement this different variational or quantum methods to solve various optimization type problems. So let me just quickly switch my screen. Hopefully you can still see it. So first of all, I wanted to go back to my initial example that I presented on Monday, which was the maximum independent set solver. For the maximum independent set solver, as we have seen, the objective was for a given graph to select a maximum number of nodes such that no two nodes are connected by an edge. This is what it means to be independent, and the maximality is a key point in the optimization side of it. What I've also illustrated is that this maximum independent set problem can be formulated as an optimization problem quadratic unconstrained binary optimization problem. Because how it works is that we have minimization, and with the negative sign, it's a minimization task. So the first sum, the sum of the individual indicators. Okay, let's also start from the beginning. Each variable z is a binary indicator, which indicates if a vertex is selected or not. So it is 1 if we put the specific vertex, the specific node, into our independent set selection. It is 0 otherwise. Therefore, if we sum up all these indicators, it gives us the size of the independent set, the size of the set we have selected. If we put a negative sign, then it will turn into a minimization problem. Our objective will be to make this number as small as possible, which means that we are selecting the largest possible nodes. The second term, this quadratic term, incorporates simply the edges. So whenever there is an edge running in between two nodes, the value of this is 1, and therefore the value u, a constant, is getting added to the cost function. So this is, in this sense, considered as a penalty term. It penalizes the action of having an edge in the selection. So if the selection is done properly, then there is no penalty term involved. None of the indicators, none of the nodes selected have an edge running in between them. So the second term becomes 0, and we can only focus on maximizing or minimizing the negative value or maximizing the positive value. So what we can do, and what this representation involves, is we can bring the maximum independent set formulation to quadratic unconstrained binary optimization representative. Therefore, we can use solvers for QBO type problems in order to try to solve the MIS problem as well. So what I've illustrated on Monday is the adiabatic evolution, which was nothing else but quantum adiabatic algorithm applied for this QBO type problem that actually solves the MIS formulation. But this is not the only way to go about this. This example is on the Pasqal documentation alongside with a second representation of it, which involves the QAOA type formulation. So we are still looking at our initial very, very simple graph with 5 nodes in this specific geometry. So I've just simply drawn out the graph to illustrate it. It's a very, very simple problem, and we are tasked at solving the maximum independent set problem for this graph specifically. Therefore, what we can do is we can construct a QAOA type algorithm for this using a neutral atom system. Bearing in mind this is and will not be the most efficient implementation, but this is still something that can be relatively easily done. The idea behind the QAOA type implementation is that you are alternating the application of two very specific different Hamiltonians as an initial guess, an initial representation. For this, we are choosing constant pulses that will alternate between mixing and a cost term. So here, the mixing is manifesting by a presence in the amplitude, and the cost part, the cost Hamiltonian, is represented by a presence of detuning parameter only. So the pulse that is being shaped is actually an alternating constant pulse. One of them has an amplitude parameter, the other has a detuning parameter only. Based on this, we can build a similar representation. The choice that needs to be made is how long these sequences last. So this is something that needs to be run through typically an optimization cycle to determine. And you also have a degree of freedom, not only the value in case of a constant pulse, but you can also play around with different shapes. For the pulses themselves. But the idea for the mixing and the co-stimulation, for a QAOA type implementation on neutral atom system, is that you're alternating between involving only detuning or only the amplitude. So you are manipulating only one of the 2 degrees of freedoms at any given time. With this alternation, alternating factor, you can try to execute the system. However, with an initial guess, what we can see here is that the solutions that come out of the system are not ideal. Actually, one of the most likely solutions is only selecting a single node and nothing else, which is obviously not a maximum independent set solution. Here I've colored with red the target solutions that we wanted to achieve. And clearly, this algorithm, this initial guess and selection of this particular parameterization is not really adapted. It's not really solving our problem. Therefore, what you can do is you can optimize the evolution by trying and testing different configurations. So you can use different optimization methods that all rely on the fact that you try to test different lengths of durations and different values for the detuning as well as for the amplitude parameter. So here what I've done is I built a simple classical optimizer that tries to find the ideal duration as well as the ideal values, still keeping in mind this particular architecture of only having constant alternating pulses between amplitude and detuning parameter. Running this optimization cycle reaches as a conclusion, again, a slightly different architecture. However, for which, if I were to execute this on my atomic register, what I can see is that the most likely solutions, the 2 most likely solutions are these 3 tri-state solutions that select the right nodes that represent the actual maximum independent set solutions. So to illustrate this, it selects 0, 0, 1, 1, 1 and 0, 1, 0, 1, 1. These are the 2 main solutions. If I go back to my graph, this means that I'm selecting not the 0 index, not the 1 index, but the 2, 3, and 4 index. So these 3 nodes are independent, and these are one of the maximum independent set solutions. The other solution from the quantum method was selecting 1, 3, and 4, so the other maximum independent set solution. So indeed, QAOA by itself for initial guesses has worked terribly. However, if we involve sufficient amount of optimization, so this variational cycle of updating constantly the parameters, we can reach a pulse sequence that provides very, very good quality solutions for our problem. Taking this a little bit further and explaining it for a different type of problematic, I wanted to showcase a little bit more the quantum adiabatic algorithm itself. So for this reason, we are really going to consider an arbitrary QBO type problem. So we are looking at the quadratic unconstrained binary optimization problem that in general is formulated as a quadratic form. I'm picking an almost random matrix. So I've defined a QBO problem by this by its representative matrix that has some random parameters involved in it. So the idea here is that my problem really comes as an optimization problem. It's not coming from graph perspective. It's not necessarily coming from a graph representation. So the natural question is, for this kind of problem formulation, how can you implement it on a neutral atoms type system? And the answer is that we will rely on the equivalence between the Kubo formulation and the Hamiltonian. So if I go back to the schematic representation, as I mentioned, there is an inherent connection between a Kubo formulation, so between the quadratic and linear terms, and the Hamiltonian representation. The Hamiltonian representation we use for a neutral atom system in particular. The encoding the representation relies on corresponding the quadratic terms with the second order terms, with the two-body interaction terms, and the linear terms with the one-body and the first one-body interaction terms, the first order parameters. So for my given Kubo problem, I only have my quadratic terms defined. And therefore, this Kubo matrix, the matrix of the quadratic terms, will correspond to the two-body interactions, which is in a neutral atom system entirely dictated by the geometry. Therefore, my task is, if I want to implement this Kubo type formulation, is that I want to find for this matrix the right position of the atoms themselves. For this, what I'm going to simply do is that I'm going to what we call embed this Kubo problem on the atomic register. We need to choose the placement of the atoms so that the distances between the atoms are a representation of my Kubo matrix. Therefore, this becomes an optimization problem that can be run on a classical resource in order to find the atomic positions that are the closest in terms of matrix representation to my Kubo matrix. So I can use various different optimization algorithms. I'm using still the Nelder-Mead type optimizer that I've used previously that tends to work quite well for these kind of purely classical optimization tasks or quantum classical optimization cycles. And this is tasked in reducing the distance between the matrix that comes out of the geometric representation of the atoms and the matrix that was given from us from the Kubo representation. And for this iteration cycle, what I find is that for my given Kubo matrix, seemingly a good encoding of my problem is the following geometry that is being proposed here. Again, the idea was that once you're given your Kubo matrix, you will use that Kubo matrix to find the appropriate geometry, to find the correct encoding of the atoms so that the matrix that arises from the geometry itself, the two-body interaction terms Hamiltonian, corresponds as close as possible to your given matrix. And then the task is simply to find a proper ground state of the system for which we can simply build an adiabatic evolution type algorithm. For this, I'm going to use a similar adiabatic evolution pulse that we have already seen on multiple occasions. Again, this adiabatic evolution relies on the fact that the amplitude parameter starts from 0, ends up in 0, and we do a shift in the detuning in order to ensure that there is a proper mixing of the quantum states throughout the evolution, and the whole duration needs to be sufficiently long in order to for the evolution to have good quality results. And what I can see here is that the solution itself, I should have changed the colors themselves because I switched from red to green, but there are essentially two solution candidates, 00111 and 01011. Do they actually correspond to the classical reference solution? Well, I have computed for that. Given for this Kubo type formulation, I've solved it classically with a simple optimizer, a very, very easy one because it's only a 5x5 matrix. You can do it by hand. And actually what you find is that the two best solutions, so the two lowest energy solutions are indeed the corresponding bit strings, so 01011 and 00111. So indeed, by selecting the right geometric encoding, the geometric encoding closest to the problem Hamiltonian, the problem matrix, and applying a simple or relatively easy adiabatic pulse, an adiabatic evolution, you can solve much more complex optimization problems as well. There does not need to be a graph theoric representation of this problem. It really can rely on purely combinatorial purely mathematical formulation as well. Are there any questions? Let me go back to... If there are no questions, let's move on to the last part that I wanted to mention for today and to illustrate, which is a concretization of these investigations in order to illustrate how close you can bring it to real-world application, these type of methods, and what are the strategies to construct much more elaborate hybrid methods or optimization methods that can be executed on various different systems. For this, I've selected a specific example from the telecommunications industry. In the telecommunications industry, they are facing a lot of optimization problems whenever they are designing telecommunications networks. So typically, designing where to place antenna in order to have the best quality service and maximizing coverage, how to avoid interference between these antennas, how to parameterize these antennas, what frequencies they need to distribute the network. All these considerations can give rise to very, very complicated optimization problems involving these networks. And whenever graphs, networks are involved, neutral atoms-based systems can give an edge, can bring about a positive impact for neutral atoms type systems in particular. The problem we are going to look at much closer is the problem of physical cell identifier, or PCI, which is sort of a unique identifier associated to the specific part of a telecommunication network. So a physical cell identifier refers to a region which is typically the coverage of a single antenna within which it's providing its services. And this is really a unique frequency, a unique tag or allocation that determines that if you as a cell phone user are within this cell, within this geographical repartition, then you get transferred to that specific antenna with that specific identifier, and then you get connected to the whole network using that identifier. This PCI, this physical cell identifier, needs to be unique in a sense that it needs to be able to allow for the network to track your movement. Therefore, for neighboring cells, they cannot have the same physical cell identifier, because if they have the same identifier, the network would not be able to tell if you are situated in one or the other. So this is the first image, the first example illustrates this prohibitory part, where you cannot have cells, neighboring cells with the same identifier. However, what's more complicated is that a specific cell, here in this case cell number 1, cannot have neighbors that have the same identifier, because this would not allow the network to be able to track your movement. So if you were in cell number 1 and were to move to cell number 3, you would need to change the PCI, the cell identifier associated to you. But if cell number 2 and 3 have the same identifier, the network would not be able to tell in which part you are physically situated. So these are the two constraints they need to keep in mind in order to allocate these physical cell identifiers. On top of that, an extra constraint is that they need to keep these physical cell identifiers as low as possible because physically they are tied to specific frequencies. So the more identifiers you have, the more frequencies you need to be able to deploy in your antenna, which is costly. It has manufacturing and maintenance costs, and it gets very, very heavy the larger the network is. So the actual task is to keep the number of physical cell identifiers to a minimum while ensuring these two constraints are respected. And to do this, an efficient strategy is to do a graph-based, constant graph-based modeling of the system. What you are doing is you have this initial geometry, the setup of your position of your antenna, and to see what is the geometric layout, who is the neighbor of who. And from that initial positioning, you actually construct a new graph, a constraint graph representation, where each node corresponds to a cell itself. So each cell gets associated to a node. However, you draw edges whenever there is some kind of constraint between them. So whenever you cannot have allocate the same identifier. To illustrate this, for instance, cells 3 and 4 are neighbors. Neighbors cannot have the same identifiers. Therefore, the corresponding nodes 3 and 4 have an edge drawn between them. Moreover, so cell number 3 has as neighbors 1, 2, and 4. These three neighbors cannot have the same identifier because, as we discussed previously, you cannot, then you wouldn't be able to track the movement between cells number 3 and the others. Therefore, for instance, for the cell number 4 at the bottom, it cannot have the same identifier as 3, which is a physical neighbor. It cannot have the same identifier as 1 or 2, which is the neighbor of its neighbor. So in the graph representation, I'm drawing an edge not only between cell number 4 and cell number 3, but cell number 4 and cell number 1, and cell number 4 and cell number 2. So you transform this geometric representation into a much more complex graph structure in order to form a graph, a new graph, what we call a constraint graph, on which now the actual task is to allocate these identifiers such that no two neighboring nodes have the same identifier, which becomes what we call a vertex coloring or a graph coloring based problem. So each color represents a unique identifier. If you're able to color with a minimal number of colors such that no two neighbors have the same color, then that coloring gives rise to a good enough allocation of these physical cell identifiers. The question here then comes into how you can solve this efficiently. So there is an intuitive greedy method that can be used for looking for maximum independent sets, but greedy methods are dangerous because they might not lead to the best possible solution. So here I've given an example of trying to color with a greedy method iteratively. So you select an independent set, you select nodes that are not connected and color them with the same color. We have colored the two opposing edges that are not connected with the same color. Then, from the remaining graph, you select a new independent set for a new color. You found one, okay. Then you continue this iteration up until you end up with decent coloring. However, the issue is that the solution you ended up with this greedy iterative method that relies on independent sets is not the optimal, because if you were to start off with a different independent set, you can find a better coloring that uses one less color even for this very, very simple 5-node graph. So the main idea here is how to construct an efficient algorithm that can provide a good quality solution. And herein comes the play that it's not enough to know how to determine independent sets. It's important to have a notion of which independent sets the method should prioritize. And therein lies the importance in constructing efficient hybrid methods because there needs to be a clear communication between the two components, so the independent set solver and the solver that builds the actual solution for you in this case. And this is something that's highly non-trivial. I see a couple of questions. Let's take a quickly yes, so there is a question about the notebook itself. Yes, indeed. So the method I presented to encode cubo-type problems relies on turning your cubo matrix into the geometry of the atomic register. In actuality, yes, for larger system sizes, it becomes increasingly more complex. Therein lies the importance of choosing the right solver, the best solver that provides a good quality solution, because first of all, you cannot necessarily guarantee the right solution. Even if you can guarantee the right solution, it might take too much time because it doesn't necessarily scale well. This is entirely the factor for choosing the right classical optimizer to find a good matrix representation. There are some very efficient techniques that can project your cubo matrix into a geometric matrix, however. So scale is not necessarily an issue if you are ready to make some compromises. Yes, so laser optimization and optimization are not necessarily the same thing. Laser optimization is really tasked in guaranteeing finding the best parameterization to find good quality solutions. For cubo optimization in particular, the task is really to encode it on the atomic register and then ensure that you can extract the right information from that. So it is actually a much more involved, much more constrained formulation. In the Hamilton representation you are referring to, I haven't touched the geometry any longer, so that was already fixed. But you can still implement, so all the implementation I've shown here, it can be implemented with analog computing. So adiabatic evolution in general is an analog construct. And so there is a last question that has some Korean elements. I'm not sure if someone can quickly translate if there is a question there or it's just observation.
Hi, I'm Ujun, and
Yes.
it's not a question, but he says using quantum harmony, you can transfer graph coloring into Hamiltonian optimization to solve NP-hard and big size data problems.
Yes. So there are multiple ways to go about graph coloring. So because we already started late, I didn't want to keep you here for too long. What I propose is that for the next session, so for Friday sessions, we are going to look a little bit more in detail on the graph coloring side and some efficient hybrid quantum classical methods in order to encode on a neutral atoms type system a graph coloring problem. And I'm also going to show an implementation for that. So we are going to discuss more on the hybrid methods for graph coloring that do not rely entirely on the Hamiltonian encoding itself. But yes, it's a very good observation that a lot of graph optimization problems can be encoded in a Hamiltonian formulation. So are there any effective applications of the quantum computing set problem? So this is an active field of investigation. You are right to point out that quantum error correction has its or can have it potentially as a component. Currently, people are still being investigating, trying to find the right methods, because problem class-wise, what we know is that it's easy to check the problem, if the solution of the problem, but there is currently no very efficient known method to solve the quantum set problem either. But this is still something that's relatively new to the field itself. Are there any other questions? If not, I propose to stop here for today. Once again, I'm very, very sorry for starting late. My apologies for that. And we will pick up the graph coloring part on Friday a little bit to illustrate a hybrid method and a hybrid implementation for that. And then we will move on to discussions about graph machine learning and quantum graph machine learning in particular. So thank you very much for your time, for waiting for me, and for your attention once again. And hopefully see you around on Friday. Yeah.